Hi Tins, and welcome to our first little science and physics video. Now that we're done with our stream study, we'll be focusing on electricity. So in this video, I'll be talking you through, we're defining electricity. We need to look at the structure of the atom to be able to understand what's actually going on with electricity. Then we'll be talking about conductors and insulators, again in terms of electricity. And the second part of the video will be all about static electricity, because that's one of the key points we need to discuss. Okay, so definition of electricity. Electricity is a form of energy, and we use it a lot because it's just so super convenient. Okay? Electricity can be transported from where we generate it, power station, to our houses through power lines. That's pretty straightforward. And once we've got it in the house, we can easily convert it into any other form of energy we might need. Okay? Here's a device that generates light, turns electric energy into light energy. Here's a device that turns electric energy into movement. Here's a device that turns electric energy into heat and movement and noise. Here's a device that turns, hopefully, electricity to sound. Enough of that. Okay, so electricity is energy, and it's so convenient because it's easily transferred into other forms of energy which we need in our homes or for certain devices. So here we go, structure of the atom. You do need to understand a little bit what an electron looks like if you want to make sense of electricity. So in the center of an atom we've got the nucleus. Within the nucleus we have positively charged particles called protons. We've got neutral particles called neutrons, and we've got tiny little electrons orbiting that nucleus called electrons, and they do have a negative charge. That diagram is really not ideal, but I can't draw it any better. Okay? The reason for that is that this nucleus is drawn way too big. If you guys imagine that this marble is the nucleus of an atom, then the atom that belongs to that nucleus would be the size of your average football stadium. So the nucleus is actually tiny in comparison to the size of the atom. And you all know that atoms are actually really tiny as well. So everything we know is made up of atoms, and I just explained to you that atoms are mostly empty space, so you're actually mostly empty space. Okay, so back to the charges. Electricity works because of charges. Now, these protons are not going to move. A proton and a neutron, the particles in the nucleus, are called nucleides. Now they're about 2,000 times heavier. They've got 2,000 times the mass of an electron. So they're heavy, chunky bits that stay in the center of that atom, and they are not going to move. But the electrons might be able to move, or they can move. But again, only the ones. I've drawn these electrons here in a couple of layers. Now, bigger atoms have even more electron shells to them, that's what we call them. And only the electrons in the outermost shell can potentially move. Okay, so it's electrons that are being removed from atoms, or it's electrons that jump from one atom to the next and to the next to the next, that generate, that cause electricity to happen. It's moving charges, it's moving electrons, to be really specific. Okay, so conductors and insulators of electricity. Now, what I've drawn here, that's meant to represent an extremely thin fiber or little piece of wire. Has to be extremely thin, because if these circles meant to represent atoms, and that's what I was trying to show here, then this fiber would be incredibly thin. Okay, you would have to chop a hair lengthwise at least 1,000,000 times, and then it's still too thick. Okay, doesn't matter. So we can see some atoms within a piece of material. Now, if I would add extra electrons to this side of that fiber or that piece of wire, if I attach that to the negative terminal of a battery, and there are electrons jumping onto these atoms, okay, so this atom now has an extra electron here. Now what does it do? Doesn't want to keep too many. If it moves it onto here, and then the electron jumps on and jumps on and jumps on, and the electrons can move through this fiber, this piece of wire, then we have an electrical conductor. A material that can conduct electricity, that lets electrons jump on and on and on and on and on through the material, is called an electrical conductor. An insulator is a material that won't let the electrons move on. So if I add some charges to this end of that fiber, then this end becomes negatively charged, but it will remain negatively charged, and these charges can't move on to the other side. So an electrical insulator won't let electric charges move through it. Now, I'm pretty sure from year 7 you all remember conductors. Usually all the conductors, or most of the conductors we ever talk about, are metals. So within metals, electrons are free to move from atom to atom to atom, and electricity is conducted. Insulators, plastic, ceramics, glass, rubber, the electrons stay attached to some atoms of that insulator, but they can't move on. That means a part of that insulator becomes charged up, but the charges won't move on. That's how we define an insulator. Now, there is one thing you might remember from the stream study. We were measuring conductivity. Now, conductivity tells you how well a substance can conduct electricity. So if I have a beaker full with water, pure water is actually not a very good conductor. So our clean river was not a very good conductor of electricity. However, if we had substances dissolved in our water, these dissolved substances, these mineral salts, fertilizer bits, cow urine, whatever it was, they actually, as they dissolve in water, split up into ions. One bit is positively charged, one is negatively charged. And now those charged particles, they can conduct electricity. So impure water with minerals dissolved in it increases conductivity. That's why we knew, as the conductivity of a stream goes up, there is stuff dissolved within the water, minerals dissolved. We don't know what they are, whether it's fertilizer, whether it's salt, whatever it is. Okay? Cool. So let's talk static electricity. This is a balloon. This is me. Okay? Now, if you want to generate static electricity, you need to rub two insulators together. I'm not really an insulator, but my hair is. This is an insulator, my hair is an insulator. So if I rub this balloon against my hair, we're getting charges. Okay? Now, this balloon is now sticking to me. I can even get a second one. Do the same over here, and we get a little Mickey Mouse effect. Okay? Now, how does this work? Let's get rid of those for a moment. Now, by rubbing the two insulators together, I will have transferred electrons from one insulator to another. Let's assume that the electrons jumped from my hair to the balloon. That means I got an excess of electrons on this side of the balloon. They can't move to the other side of the balloon because it's all made of rubber, and rubber is an insulator, as I just explained. Now my hair has lost electrons. That means each atom that makes up my hair has now more protons, positively charged particles, than it has electrons. So overall, my hair now has a positive charge. Okay? So, negative charge, balloon, positive charge, hair, they attract each other. So the hair tries to get to this balloon because the two objects have opposite charges. Key message here is opposite charges attract. Now, it's a very rainy day out there, so I'm not quite sure whether I'll manage to demonstrate this. Okay, two rubber balloons. I'm rubbing them both against my hair, so they should both have the same charge now. And if I now bring this, yes, it just works a little bit. Here we go. The green balloon is repelling the yellow balloon because both balloons have the same charge. If they're both negatively charged, there is a force, an electrostatic force, that pushes them apart. Like charges repel. Opposite charges attract, like charges repel. Key message here. Hope you remember that. Okay everyone, so here's a little trick. I've charged up my balloon. Watch the water. Pretty cool, eh? So I can deflect water with a charged balloon. Now, this is just good fun, but it is actually being used in technology. This is how an inkjet printer works. You're deflecting ink droplets by putting a charged plate close to them, and you're deflecting those droplets and you can write with them. So that's how the use by date gets onto your milk bottle or your yogurt container. Unfortunately, the one I just found here hasn't got the use by date. They must be putting it onto the lid. I very quickly find one. Here we go. That's where they're printing the use by date. As the milk zooms past on a conveyor belt, it gets printed on by deflecting little charged ink droplets with charged plates. That's inkjet printing for you. Alright guys, so let's sum up some key points about static electricity. If you want to charge up something, if you want to generate static electricity, you need to rub two insulators against each other. You rub them together, kind of friction that generates electricity, static electricity, and it'll always just be the electrons that are jumping between the insulators. So one of the two insulators will gain electrons, the other one will lose electrons. Once that happened, there'll be forces between the two charged particles. Like charges will repel. Two objects that have the same charge will repel. Opposite charges will attract. So they'll stick together, like my hair and the balloon did before. So those are the key messages. I've just talked you through the first couple of double pages I printed out from our textbook for you, which you should have had delivered to your home just before the start of lockdown. Make sure you'll have a read through those first two couple pages, please. See you later.